To look here at how you can take a reaction that you know is oxidation reduction and write an equation to show what's happening. So this is one we've already seen in previous videos, so if you've seen the oxidation one or the reduction one, sorry about the repeat here, but here we go. Here I've got acidified hydrogen peroxide, so sulfuric acid and some hydrogen peroxide, about 6%. And I'm adding a few drops of a purple solution called potassium permanganate. You can see the colour goes away straight away. So maybe I just haven't used enough and it's diluting. So I'll add a bit more. No, sure enough, it's actually reacting. You can see that on the surface. And if I get the rest of that, you can see there's still no colour. So I'm pretty confident that there's a chemical reaction happening there. How can I show what that chemical reaction is? Well, the first thing I need to do is to work out what two things I started with that could actually undergo oxidation reduction. And this is where I've got a list of oxidants and reductants to learn about. In the reaction I've just done, I had potassium permanganate. Well, the ion that's important there is the permanganate ion, MnO4 negative. I also had hydrogen peroxide, which is H2O2. Now, H2O2 is a very difficult thing to work with, to know whether it's being oxidized or reduced, because both can happen to it. H2O2 can either become oxygen when it's oxidized, or it can become water when it's reduced. Now, I already know that permanganate is a very strong oxidizing agent. That means it will cause something else to be oxidized. So I know already that it's going to be this one here. However, this early in learning about oxidation reduction, you probably don't. So, I'm going to show you how I'd do it if I wasn't sure which thing was happening. I couldn't see bubbles of oxygen being formed, so my immediate inference would be that water's being made, not oxygen. I'd expect to see bubbles if this was the reaction occurring. The fact of the matter is it's happened so quickly that I haven't actually seen the oxygen bubbles forming. They're happening too fast for me to form as bubbles. So they're being either dissolved or liberated too quickly for my eyes to see, or as too smaller bubbles for me to see. So how do I decide which one it is? Well, I work with the one that I know. Permanganate, at this level of study, we know becomes Mn2+. There's nothing else that we know of that it becomes. So we're going to balance this one and see if that's oxidation or reduction first of all. And so my manganese are balanced. Now my oxygens I'll balance with my 4 waters, my 8 hydrogens with 8H+, and then I balance my charge out with my 5 electrons. If you want to see how that's done more carefully, go back to the video on reduction, please. So this is reduction. That means this must be oxidation. So therefore, it must be the O2 one. So I've remembered that for oxidation, H2O2 turns into O2 plus 2H plus 2 electrons. Again, go back to my video on oxidation if you want to check how I've done that. So, because this one's reduction, and it's the one that I know has to be reduction, this one that could be either reduction or oxidation must be oxidation, because redox, reduction with oxidation. You must have the two hand in hand. You can't have two reduction reactions happening at once. Okay, so I'm going to get rid of my, and I'll keep those there. So now I've got my two half equations. How can I get an overall reaction or equation for what's happening? Well, I can't just add the two together because they've got different numbers of electrons. The H2O2 actually has to provide 5 electrons for this reduction to occur. So how does it do it? Well, this is where a bit of simple maths comes in. I look at my number of electrons and I aim to have the lowest common multiple here. So if I had 10 electrons on each side, then this would actually work. So what I'm going to do is I'm going to multiply the first reaction by 2. So this becomes 2, this becomes 16, this becomes 10, this becomes 2, and this becomes 8. At the same time, I'm going to do the same thing to H2O2. I'm going to multiply this equation by 5 so that this becomes 10 electrons. So I end up with 5 H2O2, 5 oxygens, 10 H pluses, and 10 electrons. So now when I put all of that together, let's see what I make. 2 MnO4 minus plus 16H plus 10 electrons. Keep going though, there's more on the side. Plus 5H2O2 goes to 2 Mn2 plus 8 waters plus 5 oxygens, 10 hydrogens, 10 electrons. Now, this is not finished. Anything that's on the left-hand side and the right-hand side must be simplified. Again, simple maths. So, 10 electrons here, 10 electrons here. They're gone. That's a good thing, because that was our ultimate goal, is to get rid of the electrons off both sides. 16 H pluses here, 10 H pluses here. Well, that means I've got 6 H pluses on this side. So I'm minus 10 off both sides. I've got nothing else in common. H2O is not the same as H2O2, so I can't simplify that one anymore. All right? So then I rewrite it again, this time without the things I've scribbled out. 2 MnO4 negative plus, I'm actually going to put the other reagent there, it's just my habit, plus 6H plus. So this is why I needed to have the sulfuric acid in there. It needed H plus ions. And there we go. You could go through and do a balance check, make sure you got the same number of atoms on each side, the same charge on each side. But I'm so confident in my process that I'm not going to bother doing that. I'd move on to my next experiment if this was an assessment. So just go through the steps again. 1, when I've got my reaction, look at the reagents. What can they become? Well, I had a confusion here because H2O2 can become oxygen or water. So I had to check with my first one, oh, this is a reduction reaction, so I have to go for the oxidation one only. I did the half equations for each of them. I then looked at the electrons, the ones circled by green, to decide whether I had to multiply the equations by anything. I did. I had to multiply this one by 5 and this one by 2 so that they both had 10 electrons. I combined. Then I looked for things that were in common on both sides and simplified. Ultimately getting rid of all electrons, the ones in the red circles there. And that is how, in principle, I balance an oxidation reduction equation.